Hey everybody, today we are going to look at momentum. So if you're taking notes, if it's blue, write it down. If it's orange, it's optional, but it's probably a good idea. And if it's gray or white, just read it. So a little bit of a recap. We've looked at Newton's laws of motion, and specifically the first law says that an object at rest will stay at rest, and an object in motion will stay in motion unless it's acted upon by an unbalanced force. This is also referred to as Newton's law of inertia. And again, we've looked at these when we talked about forces. So inertia, we measure inertia with an object's mass. If it has more mass, it resists changes to its motion more so, and therefore we say it has more inertia. If it has less mass, it doesn't resist as much, and therefore we say it has less inertia. So if you're looking to see what objects have more inertia, look for the objects that have more mass. Now I have a question for you. What would you rather try to stop? A skateboarder skateboarding towards you, or a cannonball? The skateboarder is going to have a lot more mass than the cannonball, which means the skateboarder has more inertia. And when something has more inertia, that makes it harder to stop, right? So then why would you pick the skateboarder? Well, hopefully you pick the skateboarder. If you didn't pick the skateboarder, we should probably have a talk. But you probably picked the skateboarder. But why would you pick the skateboarder over jumping in front of a cannonball? What is it about jumping in front of a cannonball that sounds like a really bad idea versus jumping in front of a skateboarder to try to get them to stop? Well, it's probably the fact that the cannonball is going really, really fast, and you're not going to be able to stop that safely. So is inertia, an object's mass, the only factor that determines what objects are harder to stop? The answer is no. There's definitely more to the story. So let's think about it like this. Let's say you have two blocks, they're the same mass, and they're moving at different velocities. One block is moving really fast, and the other block is moving really slow. The block that's going to be harder to stop is the block that's moving really fast. Now let's say you have two blocks with different masses, but they're both moving at the same velocity. The heavier block is going to be the block that's harder to stop. So we can see that both mass and velocity play a role here. Now, inertia alone explains an object's resistance to acceleration when it's at rest. But inertia alone does not account for that same object moving towards you and needing to accelerate to a stop. So if you had to push a stopped car backwards, that's going to be a lot easier than pushing the same car backwards if it's already moving forwards. It's going to take a lot more acceleration. Now, Newton realized this too, and so he came up with a new measurement. And this measurement accounted for both the inertia and the motion of the object. And this new measurement was called momentum. We can define momentum as inertia in motion. And another way to look at it is a measurement of, well, how hard it would be to stop an object. Now, in terms of variables and units, we can break momentum down. Momentum is, again, inertia in motion. Inertia is measured in mass, and we represent that with a little m. And the units for mass we use are kilograms. Motion is measured by velocity, and we use a little v for velocity's variable, and velocity, as you know, is measured in meters per second. Momentum uses a little p for its variable, and its units, as you could probably figure out, are kilograms meters per second. Again, so when looking at the units, kilograms times meters per second, we get a result of kilograms meters per second for units of momentum. Now, why is it mass times velocity? Well, we've already established that mass and velocity both play a role in how difficult it is to stop an object, so an object's momentum. Let's look at two different scenarios here. The first one with three different masses moving at the same velocity. The 1 kilogram mass, the lightest mass, would be easiest to stop. A 2 kilogram mass would be twice as hard to stop, so we can say it has twice the momentum. A 3 kilogram mass would be 3 times as hard to stop, and so we can say that it has 3 times the momentum. Now let's say we have the same mass but moving at different velocities. So instead of having different masses, we're going to have different velocities now. So the 1 kilogram mass moving at 1 meter per second squared, 1 meter per second, would be the easiest to stop. The same mass moving at 2 meters per second is going to be twice as hard to stop, and therefore we can say has twice the momentum. This same mass moving at 3 meters per second will be 3 times as hard to stop and therefore has 3 times the momentum. So momentum is directly proportional to both mass and velocity. As mass goes up, momentum goes up proportionally. As velocity goes up, momentum goes up proportionally as well. And this works in both ways. If velocity decreases, so does momentum. If mass decreases, so does momentum. So let's look at some examples here of proportionality, and feel free to pause between the question and the answer if you want to try it first before seeing the answer. So our first one, we have a car in motion and it doubles its velocity, so its velocity is now 2 times what it used to be. How much does that change its momentum by? And so the answer in this case is double, 2 times as well. So if velocity doubles, momentum is going to double as well because it's going to change proportionally to both mass and velocity. In this case, mass did not change, velocity doubled, so we see a doubling of momentum as well. Our next practice problem, if a container falls off the back of a truck, changing the mass of the truck by half, how much does the truck's momentum change by? And again, it's proportional, so if mass changes by 1/2, momentum will change by 1/2 as well. Our final example, we have a change in both mass and velocity. So if the mass and velocity of an object doubles, how much does the momentum of the object change by? Now in this case, since both mass and velocity double, we are going to see momentum quadruple or change by 4 times. Because mass changed by 2 times, velocity changed by 2 times, and therefore we have to apply 2 changes to momentum to account for the changes of mass and velocity. Momentum is a vector value. It not only includes how much momentum, but it also includes in what direction that momentum is happening. So if we look at the calculation, we have the scalar value of mass, which has no direction. It's only how much mass. But we have the vector value of velocity. Velocity includes a direction. So when things are moving and we describe them with velocity, we're describing how fast and in what direction. And that is very important with momentum as well. Momentums have direction. So when we're talking about momentum, we could have a positive momentum, we could have a negative momentum, and that becomes particularly important when talking about collision of objects, when 2 objects collide, because if they're traveling towards each other, the directions of their momentum are opposite. And so we're going to be looking at that more, but keep in mind that momentums can be positive or negative because, again, momentum is a vector value. It includes how much and in what direction. All right, we're going to wrap this up with some practice problems. Please, again, feel free to pause between the question and answer to try these for yourselves. If you need extra help, please get it. And thank you very much for watching. Have a good one.